is the disadvantage of that? The disadvantage of that is that we are having some current going through this circuit, which is basically V1 divided by R1 plus R2. And when this current goes through these resistors, especially this one, basically both of them, but like when the current goes through these two resistors, it would have some power lost in terms of heat. So the efficiency of this circuit for the purpose that we have, it's very low. We are losing so much power in terms of heat and just to step down the voltage. So that's not ideal. Like it would do the job for us. It can step down the voltage, but we're gonna lose so much power. So that's the other point I wanted to mention. Similar to voltage dividers, we have commercially available tools that are called voltage regulators, linear voltage regulators. These are basically similar to voltage dividers. Not exactly the same, but very similar. So if you look at this adapter, this is gonna, it's an adapter that would convert an AC voltage to 9 volt DC voltage with 1.3 amp output current. But this thing that my friend Dr. Jalal has attached to this, and it's not very safe, so don't do this at home. This basically is called a voltage regulator. This is a device that's very similar to voltage divider and converts a DC voltage to another DC voltage, and you can use it to reduce the voltage. So, and we have put a capacitor here, like my friend has put a capacitor here to maintain the voltage. So this would basically convert that 9 volt output of the adapter to a 6 volt DC voltage. So it's a step down regulator, but it's not efficient. It's not very efficient. It would the efficiency of it is very low. It would have some current going through this, and it would generate some heat. So if I connect this to power, you would see that this thing would just heat up, and so much power is going to be lost. So what is the solution? The solution is using switch mode power supplies. What's a switch mode power supply? We saw that in the boost converter. So switch mode power supply is when we have a voltage, let's call this voltage input voltage, and using some switches we basically create pulses. So we would just apply this voltage to the circuit for a certain period of time, and then it would be disconnected for another period, or like duty ratio. So that's what the switch mode power supply is. Now, one thing that I want to remind you again is the concept of volt-second balance for inductors and amp-second balance. This is volt. Concept of amp-second balance for capacitors. So let's say that like we have a switch mode power supply that we turn the switch on for the duty ratio of D times the period, and it's on for this much time, and it's off for 1 minus D times T. So in many of the analysis that we do, we assume that we are in the steady state mode. But our steady state mode is not like the DC steady state mode that you would have. Let's say like this is like transient, this is steady state. That's DC, like when you have no changes in the current or voltage. The steady state mode that we have is the average steady state, or also called AC steady state. It means that things don't change over the period, like the average of our parameters are the same over the periods. So if we assume that we are in this AC steady state, then based on the dynamics of an inductor, excuse me, our average voltage should be 0, right? If we are in the steady state, our average voltage should be 0. So it means that also DIL over DT average, it's going to be 0. So these are like two things that we have to remember. So the average of the voltage across the inductor, it's going to be 0. And the average rate of change of current, it's going to be 0. This thing basically tells us that the current at the beginning of the period should be equal to the current at the end of the period. And having the average voltage equal to 0, it basically means that if our voltage, let's say if the voltage of the inductor changes like this is not a very good scale. So like if it's like this, it means that over one period, if you take the average of the inductor, and you know that like how to calculate the average of parameter. The average of a parameter is 1 over t integral over the period of that parameter, VL dt, over time, right? So this has to be equal to 0. That means that this basically represents the area, this area has to be equal to 0, or in another case, this area A1 has to be equal to A2. What happens if we don't have volt-second balance? If we don't have volt-second balance, let's say that we have a voltage across the inductor that's always constant over the period. Or let's just assume that it's like it's this much and then gets 0 and then this much, right? If that's the case, this area plus this area, of course it's not 0. It's a positive value. So it means that voltage, average voltage across the inductor is a positive constant. So it's a constant, right?